In this video, we present a simple GPT-style AI transformer in C++. We have covered most of the underlying programs in the previous few videos, which could be found at this link. Here we bring them together to implement a complete GPT-style transformer in C++. We also provide a simple training example. When executed, it prints out the entropy loss at selected poles. As you can see, the loss decreases steadily over the course of training. After training, if we input English digits such as 1, 2, 3, the model generates the corresponding Spanish digits, like 1, 2, 3. Billy will first give you a concise review of a general transformer and explain the principles of a GPT-style transformer.
This figure illustrates the transformer architecture. On the left is the encoder, which repeats 6 times. On the right is the decoder, also repeating 6 times. Thus, we have 6 encoder layers and 6 decoder layers. The final output of the encoder is denoted as E. This vector is fed into the multi-head attention mechanism of each decoder layer. The external input to the decoder is X, and the output at the first decoder layer is X1, the output at the second layer is X2, and so on. We can label the output of the final decoder layer as X3, or Y, which then passes through a linear layer and a softmax. If we expand the encoder stack, it looks like this. Input goes to encoder layer 1. Its output feeds into encoder layer 2, whose output feeds into encoder layer 3, and so on. The final output of encoder layer 6 is E. And as shown, E is passed to the multi-head attention blocks of all decoder layers. Similarly, the output of decoder layer 1 is passed to decoder layer 2, and so on. All decoder layers operate in parallel with respect to receiving E, but sequentially in terms of their own internal connections. Note that only the final output, that is, the output of decoder layer 6, goes to the linear and softmax layers. That, in essence, is the basic architecture of an AI transformer. After embedding and positional encoding, a transformer begins its forward computation starting from layer 1, passing outputs sequentially to the next layer, as illustrated in the figure. In our decoder layer, we use index 1 to refer to the first multi-head attention block, masked self-attention, and index 2 to refer to the second multi-head attention block, cross-attention. We denote the input to the decoder, or the input to the first block, as X. After the first block, the output is X1. After the second, cross-attention, block, the output is X2. The final output, after passing through the feed-forward network and the final add and norm layer, is Y, or X3. The encoder's final output, E, is used as the key and value inputs to the decoder's cross-attention blocks. Once forward computation is complete, the transformer performs backpropagation to update all weights and learnable parameters. It uses the difference between the softmax output probabilities and the target labels to compute a loss gradient. This gradient updates the parameters of the last layer and is then used to compute another gradient for the layer below, repeating this process down through the network. We discussed this backpropagation process in detail in the previous video. A GPT-style transformer is a decoder-only transformer, meaning it consists of solely decoder layers. It has no encoder and no cross-attention, only masked self-attention. Its core task is to predict the next token given the previous tokens. A decoder-only transformer has the following advantages. 1. It has a simpler architecture as it does not need an encoder and cross-attention, so it has fewer components and thus easier to implement. 2. It has a unified framework, which is very flexible. Everything becomes text-to-text continuation. This flexibility allows you to perform translation, summarization, or code generation simply by formatting the input appropriately. 3. It has efficient inference. At inference, it only needs to process new tokens. With key value caching, generation is very fast. 4. It scales very well. More data simply calls for a larger model, which leads to better performance. 5. No alignment is required. While an encoder-decoder model requires explicit source, target pairs, a GPT model can be trained on raw text alone. This makes large-scale training much easier. On the other hand, the model has the following disadvantages. 1. It is not naturally suited for input-output tasks. Translation, for example, ideally requires an explicit separation between source and target. In GPT, this separation is implicit, not structural. 2. It requires masking tricks. Loss masking is needed so that only target tokens contribute to the loss. In contrast, encoder-decoder models have a clean separation between input and target, requiring no masking. 3. The model is less efficient for long inputs because it attends to both the source and the generated tokens together. 4. It has weaker alignment for translation. Encoder-decoder models use cross-attention to directly align source and target. GPT must infer this alignment implicitly, making precise translation more difficult. 5. The model could have exposure bias during generation. During inference, the model uses its own predictions and errors could accumulate over time. 6. It needs more data as the model must learn the task, the language, and the alignment all at once, demanding larger datasets. In general, the model works best for language modeling, chat systems, code generation, and general-purpose AI. It is less ideal for strict translation, structured input-output tasks, and low data scenarios. The following table provides a comparative summary of the strengths and weaknesses of decoder-only architectures versus encoder-decoder transformers. Below is a complete implementation of a simple decoder-only transformer in C++. We discussed most of the functions before.
Thank you, Billy. Below is a full implementation of a GPT-style transformer in C++. These are the helper functions. The header file util.h. We declare a two-dimensional vector of double to be matrix D. D here means double. Let's go to the implementation util.cpp. So F is an activation function. We use VLU or verified linear unit as an activation function of a single variable double C. So we return the maximum of 0 and C. And VLU is the VLU activation function with matrix input. So it returns a matrix. And VLU deriv is the derivative of a VLU function. Okay, again, the input is a matrix, okay, and returns a matrix. So basically, if the element is larger than 0, then the derivative is 1, otherwise it is 0. Very straightforward. Coarse entropy calculates the entropy loss using the probabilities input and the target tokens. Okay. It uses this formula. Add mat is to add two matrices and returns the sum. Transpose compute the transpose of a matrix A and returns the transpose. matmul performs matrix multiplication and returns the product, like C is equal to A times B. Scale mat is to scale a matrix A. So basically we multiply all the elements of the matrix A by a constant S. So the content of A, matrix A is altered. And multi-mass, basically that's the same thing, but it does not change the content of A. So A is constant. Okay? So instead, if it creates a new matrix B and returns the scaled elements contained in B. Init matrix is to initialize a matrix M with dimension n times m using some random values, using the function normal distribution. Okay? We use a sigma of 1 over 16 okay, to do the initialization. Print dictionary is to print the pair, string, and in of an unordered map. And print matrix prints out the matrix elements, okay, which are tuples. Add norm, add and norm is the modular add and norm we discussed before. Scaled attention returns the attention calculated from the inputs Q, query, K, the key, and V, the value. And we also have a mask, which could be true or false. That means with or without mask. So if it is masking, mask equals true, okay, then the upper elements, upper triangular elements will be set to negative infinity. So this is the function causal mask. In general, okay, matrix S, we set the upper triangular elements to be negative infinity. And update weight is to update the weight matrix W using the delta W, the dW here, with learning rate eta, using this formula. Clipped is to ensure that the elements in a matrix won't be beyond certain maximum value, or won't be less than some negative value. Softmax is a softmax activation function. Here we have a 1D input vector, and it returns a 1D vector tuple. And here the softmax has a matrix input. That means the input is a 2D vector, and it returns a 2D vector also, returns a matrix. And softmax derivative carries out the computation of softmax derivative, okay, using the formulas we discussed in the previous video, okay, and returns the values in the matrix form, DLDS. The implementation of a decoder-only transformer classes is based on this figure. We call the final output layer consisting of the linear function and softmax function. Okay. Linear is basically a matrix multiplication of weight and the input. And we call this block GPT block. It consists of masked multi-head attention and norm, and there's no coarse multi-head attention. This goes directly to feed forward and then to another norm, and this repeats n times. In our example, we just use 2 layers. That means n equals 2. And also we call this norm 1 and this norm 2. We also have positional encoding and embedding, and before that is tokenization. The label inputs here refers to the source sequence. The outputs here refers to the target sequence. Shifted right here refers to the target input sequence being shifted right by 1 position relative to the original source sequence. During training, the model predicts the next token given previous tokens. The input to the decoder is the same as the target sequence, but shifted right by 1, so that for position I, the model sees tokens 1 to blah blah up to I minus 1, and it must predict token I. This file, transgpt.h, is the header file of all the classes. It contains the interfaces of all the classes. This is the tokenizer class. It has the unordered mapped string in words, okay, and unordered mapped in string word index, okay, and n token is the number token, number words. Okay. And there are some special tokens we consider: PAG for pad, UNK for unknown token, BOS for beginning of sequence, EOS for end of sequence, SEP for separation, and the private function add-word is to add the words in a sentence to the words variable, to these words. Split is to split a string into different words. And these are the member functions of a tokenizer. And this is the embedding class, and tokens number words or the sequence length. Dim is the embedding dimension. And matrix is the embedding matrix. and these are the member functions, and positional encoding, and so the PE here is the positional encoding matrix. So the add PE is to add embeddings to the positional encoding matrix. This is add norm. So we discussed all this in previous videos. Feed-forward network class with weights W1, W2, and the dimensions D model and DFF. And this are cache F1 and C. Constructors and member functions with backpop. This is the multi-head attention class. So we divide the attention into heads. Okay, so basically DK is D model divided by N hex. And so we use a vector to save all this WQ, WK, WV. These are per head okay, for WQ, WK, WV. But this is for the whole. And we cache all this QS, KS, VS, PS, P property, A the attention, V the value, K the key, Q the query. We save all these matrices in a vector for each head. And the member functions. And this is the output layer we just discussed. So, and this is the GPT block we just mentioned. Okay, it is this block in this diagram. This whole thing. So you have two and norm, if feed forward, and masked multi-attention. So this GPT block, the masked multi-attention and norm 1, okay, the feed forward network FFN, and the other and norm 2, and then the forward, backward computations. And we declare a mini GPT to have all these features, the embedding, positional encoding, and the GPT block layers. So we have 2 layers in our example, and then the output layer, this output, the final output, and sequence length, vocabulary size. And this is the constructor and the member functions again. The forward is the forward computation. Now this is train step, is to train the transformer. Let's discuss that also. This file, transgpt.cpp, contains the implementation of the member functions of the classes. This is the tokenizer class, a default constructor, and a constructor to build the vocabulary from a file. So the IF stream is an input, and tokenize is to tokenize a string. It returns the token IDs in a vector. The tokenize works the opposite. It takes a vector of token IDs and returns all the words in the form of a string. This is the embedding class. We discussed all this in previous videos. Positional encoding class, an norm class. So an norm class has a forward computation and also a backward propagation. We also discussed this in previous video. This is the feed forward. Again, it has the forward computation. Here we call it FF out. And back propagation. This is the multi-head attention. It starts with a D model n heads, and dk is D model divided by n heads, and then that's the initialization of the weights. And then we split the heads, okay, the matrices to heads, and also apply the mass and do the scaling. And save all this A, the result in a vector called heads. And this is the back propagation routine of the multi-head attention. And this is the output layer. There's the final layer of the transformer after the GPT blocks. So in the output layer, the forward computation will give us the probabilities. So first you get the notches from X and W, that's the linear, and then using the softmax functions, we get the probabilities. And in the output layer, yes, the backward propagation routine, so it returns dl dx for the GPT block. So all these dl dx will propagate backward. So this is the GPT block. That's basically the GPT-style transformer, decoder only, no encoder. So in the forward computation, it goes through the first compute attention, goes a norm, and then feed forward another a norm. In the backward computation, it starts from the top a norm, that's norm 2, to the back pop, and then goes back to the feed forward, okay, and then pass back to the norm 1, and then we do the final back pop and return the result. So this is the mini GPT, where we create a GPT block and we save the GPT block in the layers, the vector layers. Okay. So we have 2 layers. That means 2 GPT block. Each layer is a GPT block. For each layer, Yes, a forward computation. Yeah. And backward computation. Now this is the train step, the training a transformer. The inputs of train step are a vector of token IDs and the learning rate eta. From this vector, we create input and target. As we mentioned earlier, in a decoder-only transformer, the input and targets are not structured. They are mixed together. So the input is from the beginning to the n minus 1. And target is from beginning plus 1 to the n. Okay, it is shifted by one position. Okay. Say for example, say the input sequence could be the special token SOS and 1, 2, and then the target sequence is shifted. It is 1, 2, 3. And we do the embedding of the input, so we get X, and then do the positional encodings. Okay, so add PE to X. And we create a vector to cache the outputs from each layer. So each layer is a GPT block. Okay. And so we also call the output to be X, and we put that in cache. And actually here we only have 2 layers. And from the output layer, we obtained the output. So the output is obtained from the final output of the layers of the GPT block. Okay, so we put the final output to X, and then we get the probability P. Okay. Now, some remarks for this probability. Now, at position I, the model takes tokens 1 to I minus 1 from the input, as we just saw, and outputs probability distribution Pi over the vocabulary. And target I is the correct token at position I. So Pi target I would be the probability model assigned to the correct token. And from this probability, we can calculate the loss using this function cross entropy we discussed earlier. With P, this matrix probabilities, and the target, this target. So basically, if the probability is high, the loss is low. That means accurate prediction. On the other hand, if the probability is low, poor prediction, then we have a large loss. And as we discussed in the previous video, actually the loss is not necessarily needed in the calculation of backpropagation. We just need the gradient loss, and the gradient loss, that means the dl dx, for example, and it is computed from P, probability P, and the target. Okay. And from the output layer, we do the backward propagation. Okay, using these values xp target and returns the LDX. The LDX will be used for other further backward propagation. Okay. So for all the GPT blocks layers. Okay, and then return a loss that's for reference. Lastly, we provide a program test main.cpp that contains a main to test the above transformer, which is decoder only. This is the main. Okay. First, use the tokenizer class to build up the vocabulary. The vocabulary is in the file t.txt. It contains some English digits and the corresponding Spanish digits. And it prints out the vocabulary size. Now, this is our model. In our model, we use the sequence length to be 50. That's the maximum sequence length the model can handle. And the dimension of the model is 32. Number of heads is 4. DFF is the dimension of the feed-forward network is 128. N layers, the number of layers of the GPT block in the transformer is 2. So we create an object of mini GPT using these parameters. And to train the transformer, we need to provide the data set. So we create a 2D vector, a declared 2D vector data set. Okay. And we put data in this data set using this function build data set with the tokenizer. The tokenizer contains the vocabulary. Okay. And this function build data set will return the data set, okay, that we built. Okay, so the build data set is this function, so it's hard coded. Okay, very simple. So the tokenizer contains the vocabulary. So we create this 2D vector data set, 2D in vector. So that will contain the token IDs. So this is the string 1 to 3 and the corresponding Spanish digits. 1, 2, 3. So we first tokenize this. So this will be changed to integers, token integers or token IDs. So we push this vector. Now this token IDs is a vector of tokens, okay, or token IDs, okay, of this sentence or this string. Okay. So this is one set of data. Now we try another set of data, 2, 3, 4, and the corresponding Spanish digits, and again tokenize that and push that into the data set. Okay, so this is a vector of IDs, and another training data set, data string, okay, and then again put that into data set, and so on. So there's a very simple data set. So we return the data set. So the data set contains the tokens that we need. And now this is the training loop. So we create a variable loss, and now we use the keyword auto to and the sequence, okay, of the data set, okay, is a 1D vector actually, but this is a shorthand of writing that, okay, auto, okay, automatically C++ will return the correct data type. And so we use this vector of token IDs, or sometimes we call it tokens, to train the model. With eta, there's 0.002, and for every 20 times of training, approach mod 20 equals 0, we print out the loss, okay, and see how the training goes. Okay. Now after training, we can try the model. So that this is the inference. Suppose we provide a prompt 1 to 3, and we first we tokenize that. Okay, tokenize this prompt to get the token IDs. We print out the prompt, and we generate. We use the function generate, calling the model with these prompt tokens, okay, the tokenized prompt, okay, with the 3 extra values, okay, and we print out the generated text. Okay, now the generate is here. Now this is generate function. We pass in the model the token IDs. We call it prompt. Okay, we for simplicity, okay, and this is the maximum length that we want to generate. Okay. So we create this vector tokens to be prompt. And then we basically try to extract the most likely predicted tokens. Okay. So we create the input to the model from the, so this is a vector of in, okay, using the tokens from begin to end. Okay, this input contains all the tokens, okay, and then to use the model, the forward, to get, okay, with this input, okay, this input, okay, to get our P, our probability. And then with this probability, okay, we create a vector double. Okay, the P, the back, okay, means that we get the last row of this matrix P. Okay, it's just the last row. Okay, so the last here contains probability distribution over the vocabulary for the next token. Okay, and each index in last corresponds to a token ID in the vocabulary. So we try to get the one with the maximum probability. So we use a liquidity decoding method. Use this element, max element, from last this last begin to end to iterate through the list. And this function, max element, will return an iterator pointing to the maximum element. Okay. And then we minus last begin. So by minus last begin, this converts the iterator to an index. Okay. And this index corresponds to a token ID. And we save this this token, okay, in the list. Okay. And at the end, we return the tokens. Okay. So there's the generated that generate what we enter. Okay. And now, so we tried 1, 2, 3. So we expect it would generate the corresponding Spanish digits for 1, 2, 3, and also 3, 4, 5. Okay. So now let's copy and try this all these programs. We also provide the make file that compiles this program testme and the classes and util programs. Okay. Now let's copy them and try them. I've just copied all these files to this directory. Let's display them briefly. Okay, the utilities. Add the file of transGPT. And the programs and the classes. Okay, the testme. Okay. And this is the make file. Okay. So now we can make. So this creates the executable testme. Now this is our vocabulary t.txt. Okay, so it contains the English digits 1 to 10 and the corresponding Spanish digits. Now we can execute this. You can see that the loss decreases along the training. Okay. And say for the prompt 1, 2, 3, so the general text will be 1, 2, 3 and uno, dos, tres. And if the prompt is 3, 4, 5, then it also generates the corresponding Spanish digits. Yeah. Now, actually, we can replace the Spanish digits by Arabic digits. So I've saved this in TAM. Okay, we call this t1.txt. And slightly modify the program to test may1.cpp. So our test one is like this. Okay, the Arabic digits, okay, and the English digits, and this the training. The build sequence, okay, is modified, and of course the input file is changed to t1.txt, and this becomes Arabic 1, 2, 3, and 2, 3, 4. Okay. All others are the same. Okay. Now if we compile this, the program now is test main 1. Okay, so it compiles. Okay, and let's execute this. And again, the loss decreases along the training, and again it generates the correct form. 1, 2, 3. You get this 1, 2, 3, and 3, 4, 5. We get the Arabic 3, 4, 5. Okay. So this wraps up our discussion on this topic. You can try the programs yourself and modify them and see how it works. Okay. Well, thank you for watching, and I will see you in the next video. Okay, bye.